Welcome to Book Nibbles. Big ideas, small bites. Stephen Hawking's A Brief History of Time is one of those rare books that manages to bridge the vastness of cosmology with the curiosity of ordinary readers. In it, he takes us on a journey across the universe, not only in space but in time itself, while always attempting to make sure that we are not entirely lost among the equations and paradoxes. His goal is not to dazzle with inaccessible mathematics, but to bring us close to the great questions: where the universe came from, how it works, and whether we can ever hope to reach a final understanding. Retelling this work is like walking with Hawking through the history of human thought, where each step toward scientific discovery reshapes our understanding of reality itself. The story begins with mankind's most ancient fascination, the night sky. For centuries, humans looked upward and asked the simplest, yet most profound questions. Where did the stars come from? Do they move, and if so, why? Is the Earth at the center, or just another piece in a grander pattern? Hawking carefully reconstructs the shift from Aristotle's Earth-centered universe to Copernicus' radical heliocentric model, showing how science began to free itself from purely philosophical speculation and base its claims on observation. Galileo's telescopic evidence and Kepler's precise description of planetary orbits set the stage for Isaac Newton, whose laws of motion and gravitation gave mankind its first coherent picture of a universe governed by predictable principles. Newton's triumph was that the heavens no longer seemed mysterious. They followed the same physical rules as objects on Earth. But even with Newton's success, deep mysteries remained. What kept the stars burning? Was the universe infinite or finite? Would time run forever, or had it begun in some distant moment of creation? Einstein enters Hawking's narrative as a revolutionary figure, showing that Newton's laws, though powerful, were not the final story. With the theory of relativity, space and time were no longer separate, absolute backdrops against which events played out. Instead, they were woven together in a flexible fabric called spacetime, distorted by matter and energy. Suddenly, time itself was relative depending on how fast you moved or how strong a gravitational field you were in. For everyday life, these effects are tiny, but across the cosmos they are decisive. Relativity brought new possibilities: the expansion of the universe, the slowing of time near massive objects, the bending of light around stars. And relativity, combined with quantum mechanics, the strange rules governing subatomic particles, would eventually lead to predictions that strain even our imagination. Hawking brings us to one of the most startling discoveries of the 20th century: the universe is expanding. This idea, first observed by Edwin Hubble, meant that galaxies are moving away from one another, like raisins carried apart in a rising loaf of bread. If you reverse time, it implies that at some distant past moment, all matter and energy were concentrated in an unimaginably dense state, the singular beginning we call the Big Bang. This wasn't simply a question of things moving outward into space. Space itself was stretching, carrying galaxies along. The Big Bang theory implied not only a starting point but also raised questions of whether the universe would expand forever or collapse back in a big crunch. Hawking shows how these possibilities depend on the density of matter and energy, and how observations suggest that the expansion is not slowing in the way we once expected. The Big Bang also leads directly into the problem of time itself. If time has a beginning, what does it mean to talk about before the universe? Hawking uses an analogy. Asking what was before the Big Bang is like asking what lies north of the North Pole. Time, as we know it, may have begun with the universe itself. But he doesn't simply leave it at that. He explores models in which the boundaries of time are not sharp edges but curved surfaces, where time could be finite yet unbounded. These are not easy ideas to grasp, but Hawking's narrative keeps drawing us back to the central point. Physics is not just about what exists, but about what it means for time and space themselves to exist. One of the most compelling sections of Hawking's journey involves black holes. Formed when massive stars collapse under their own gravity, black holes represent regions where spacetime curves so steeply that nothing, not even light, can escape. For years, scientists believed black holes were perfect prisons, hiding their contents from the outside world forever. Yet Hawking, through a brilliant use of quantum mechanics and relativity, showed that black holes are not entirely black. They emit faint radiation, now called Hawking radiation because of quantum effects at their boundaries. This discovery was radical because it meant black holes could eventually evaporate, releasing the energy they had swallowed. It also raised the profound information paradox. If black holes destroy all information about what falls into them, then the fundamental laws of physics that require information conservation would be broken. Hawking's willingness to follow the mathematics, even when it led to paradox, reflects his scientific courage. Throughout the book, Hawking alternates between explaining the progress of cosmology and reflecting on what it means for human understanding. He explains complex concepts, like the uncertainty principle, which states that we cannot know both the position and velocity of a particle precisely, not merely as mathematical curiosities, but as foundations for why the universe has the form it does. Quantum mechanics, with its probabilities and uncertainties, does not fit easily with the deterministic picture of relativity. Reconciling these two pillars of physics into a single coherent theory of everything remains the great challenge. The search for such a unified theory drives much of the narrative, with Hawking exploring candidate approaches, such as string theory, which proposes that the basic constituents of matter are not point particles but tiny vibrating strings existing in more dimensions than we perceive. One of Hawking's gifts as a storyteller is his use of metaphors. He compares the universe to a balloon expanding, with galaxies like dots on its surface moving away from each other as the balloon inflates. He likens the uncertainty principle to trying to measure the exact position of a particle with light, only to find that the very act of measurement disturbs the particle. These illustrations make abstract physics feel less like distant theory and more like an extension of human experience. But the book is not only about physics, it is also about philosophy. Hawking frequently returns to the question of whether the universe needs a creator. If we can explain the origin and laws of the universe entirely through physics, does that leave any room for divine intervention? He does not dismiss the question but frames it in scientific terms. A complete theory would not eliminate God, but it would make God unnecessary as an explanatory force. Still, he admits, even if we discovered such a theory, the ultimate question, why there is something rather than nothing, might remain beyond science. Another fascinating theme is the arrow of time. Hawking distinguishes between three different arrows: the thermodynamic arrow, where disorder, entropy, increases over time; the psychological arrow, which is our perception of time always moving forward; and the cosmological arrow, which is tied to the expansion of the universe. These arrows generally point in the same direction, but he wonders what would happen if the universe eventually collapsed. Would time reverse? Would people remember the future instead of the past? Though the speculation is playful, it points to real questions about the deep structure of time. Hawking also examines the limits of prediction. Even if we had perfect knowledge of physical laws, quantum uncertainty means we could never predict everything with absolute certainty. At best, we could know probabilities. This recognition reshapes the way we think about determinism. Laplace once imagined a demon who, knowing the position and momentum of every particle, could predict the entire future. Quantum mechanics dismantles this dream, suggesting instead that the universe is inherently probabilistic. For some, this randomness is troubling, but Hawking presents it as a natural feature of reality, not a flaw. Toward the end of the book, Hawking reflects on the quest for a final theory. Science has made extraordinary progress, yet we still lack the unified framework that can seamlessly connect quantum mechanics and relativity. He describes the dream of a theory of everything as not only a scientific goal but a human aspiration, to know the mind of God, as he famously puts it. This is less a theological statement than a poetic way of expressing the hope that humans can understand the deep order of the cosmos. The beauty of A Brief History of Time lies not only in its subject but in its tone. Hawking, despite the immense challenges of his physical condition, writes with humor, warmth, and humility. He peppers the narrative with playful asides, like noting that publishers told him every equation he included would cut sales in half, so he limited himself to just one: Einstein's E equals mc squared. Such touches remind us that behind the cosmic scale of the subject stands a very human guide. By the conclusion, Hawking leaves us with both knowledge and wonder. We understand better how the universe began, how black holes behave, how time and space intertwine. But we are also reminded of the mysteries still unsolved. His central message is that science is not about reaching a final answer, but about the ongoing process of deepening our understanding. Each breakthrough opens new questions, and each question brings us closer to seeing the universe not as something alien, but as the stage on which we ourselves are part of the story. In retelling Hawking's masterpiece, one feels both the weight of human curiosity and the lightness of discovery. The universe, vast as it is, becomes something we can at least partially grasp through reason and imagination. And that, perhaps, is Hawking's greatest gift, showing that even the most profound truths of space and time can be approached not only by scientists in laboratories, but by anyone willing to wonder. And that's it. Stephen Hawking's A Brief History of Time. Thanks for listening to Book Nibbles. If you enjoyed this bite-sized book, don't forget to subscribe for more quick, insightful summaries. See you in the next nibble.